Hello again. Today we're going to talk about moments and center of mass and how integrals can be used to help us find these items. Many structures and systems actually behave as if their masses were concentrated at a single point. We call this point the center of mass. And so we need to determine how we locate this point. So we're actually going to work with only one and two dimensional objects. So in this section I'm not going to derive the formulas. For the development of these formulas you can actually research this in another textbook or online. So let's start with what's called the moment, mass, and center of mass of a thin rod or a strip along the x-axis. And generally a piece of material has what's called a density function that describes it. So we're going to pretend like we actually don't know what that density function is, so we're just going to call that function delta of x for density. And so these are only for one-dimensional object. So for instance, if you have a strip, that would be one-dimensional. So we're going to be looking for the center of mass of this particular object. Okay, so first we're going to identify the moment about the origin. And so the moment about the origin, we call that MO, or M sub O. And that's actually equal to the integral from a to b x delta x dx. And then we identify the mass. Well, to get the mass, all you do is integrate the actual density function from a to b. Now when we say a to b, I'm talking about from the left endpoint to the right endpoint of the strip. Okay, so that's what a to b is. And from those two values, you can actually get the center of mass, which we will call x bar. So basically, you take the moment about the origin, then divide it by the mass, and that's going to give you center of mass. So let's go ahead and look at an example. So the next example says prove that a center of mass of a straight thin strip that has constant density lies halfway between its two ends. So let's just pretend like this strip right here is our thin strip. And so we'll say it starts on the left endpoint at A and on the right endpoint will be B. And so we want to show that the center of mass falls halfway between A and B. Okay, so going back to what we learned up here for a one-dimensional center of mass, the first thing we have to do is find the moment about the origin. Now the moment you integrate from A to B, x times the density function. Now since the density function is constant, I'm going to let k represent that density function, and that's, as I said, that's a constant. So now when you integrate this, you get x squared over 2. It looks like I left out the k there, but you get x squared over 2 times k. And so what we'll do is we'll just assume k sits outside of the calculation for the integral. And so if we evaluate this from a to b, we'll actually get b squared over 2 minus a squared over 2, which is basically the same as saying b squared minus a squared over 2, and then of course times the density function k. Alright, now we also have to identify the mass. So go to this formula up here and get the mass. Well, the mass is you're simply integrating the density function from A to B. So since the density function is a constant, we actually would just get the constant times x from A to B. And then so when we evaluate this at B, we get KB. When we evaluate A, we get KA. So you have KB minus KA, and of course we can factor out the k and just get b minus a over k. Now, so what we have to do here now to find the center of mass is to get x bar, we take what we got for the moment about the origin, m naught, and divide it by the mass, m. So basically, if you take here's what we got for the moment about the origin, and then down here's what we got for the mass. And so if you divide these two, well, the first thing I notice is that the constant actually cancels, and basically we can rewrite this like this, where you factor the b squared minus a squared into b plus a, b minus a, and then it's going to be over 2 times the b minus a, and then you can cancel the b minus a's here, and you get b plus a over 2, which is actually half the distance between a and b. So b plus a over 2 is actually the midpoint of the interval from a to b. So we did it. We showed that the center of mass lies halfway between the two ends. So here we have the next example. We have a 10 meter long rod that thickens as you go left to right. So here it's narrow on this end, and we'll actually say this is 0, and then it gets thicker as we go farther out on the length. So we'll say that it's actually 10 meters. And so the density is actually given as a function of x. So let me go ahead and show you the density function. So the density function is actually just 1 plus x over 10 kilograms per meter. And so that represents the density. So now, so it would appear that on this example, since we don't have this consistency we had up here on this other example in the density, it would appear that the center of mass wouldn't actually be right in the middle. So let's see how we can do this. First, we're going to find the moment about the origin. So the moment about the origin, we would integrate from 0 to 10, and then using the formula x times the density, and when you multiply that, you get x plus x squared over 10, and then when you integrate this, you get x squared over 2 plus x cubed over 30. And then if you evaluate this from 0 to 10, I really just have to evaluate it at 10, because if I plug 0 in, both these terms are 0. So if I evaluate it at 10, I get 100 over 2 plus 1,000 over 30. And if we add these two together, 100 over 2 can actually be written as 1,500 over 30. So if you add them together, you get 1,500 over 30 plus 1,000 over 30, which is 2,500 over 30. And that reduces to 250 thirds kilogram meters. Okay, so that's the moment about the origin. Now the mass, you simply just integrate from 0 to 10 the density function, and I'm assuming you guys know how to do this. So you integrate 1, you get x. You integrate x over 10, you get x squared over 20. And then if you evaluate that from 0 to 10, again, when you evaluate at 0, both terms are 0, so we just have to evaluate at 10. So I get 10 plus 100 over 20, which is 10 plus 5, which is 15. So the mass would be 15 kilograms. So now to find the center of mass, I just take the 250 thirds for the moment about the origin, and then divide it by the mass. And then you can invert and multiply, so that would be 250 thirds times 1/15th, which would end up giving me 250 over 45. And then I can reduce that to 50 over 9. And then I went ahead and just divided it out and got a approximation to 2 decimal places. So it would be at 5.56 meters. So let's just say that this is the halfway point. Okay, so in this example, the center of mass is a little bit farther than halfway. So your center of mass would probably be somewhere in here for the x value. So a little bit farther than 5, somewhere between 5 and 6 meters. Okay, so I think this is a good point to actually shut this video down. And then on the next video, we're going to continue this discussion talking about that mass that's distributed over a plane region, so therefore we would have two-dimensional applications rather than one-dimensional applications. So I'll see you again on the next video to discuss that.